we have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
You're looking at live footage of an Ariane 5 rocket in Kourou, French Guiana. At the very top of that extraordinary machine, one of the largest rockets in the world, we find the most ambitious space observatory ever built, the James Webb Space Telescope. And today is launch day. From all of the people all around the world working on today's launch, good morning, bonjour, buenos dias. This is live coverage of the historic launch of the James Webb Space Telescope. I'm Michelle Thaler, speaking to you from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And I am very excited to be with you today. Today, the James Webb Space Telescope begins its journey to explore the edge of our observable universe, and its journey into history as well. This launch has been years in the making, and the world has turned out to watch. We'll have a lot to discuss both before and after launch, but let me set the scene for what's going on around us. While I'll be anchoring coverage from here at NASA Goddard, the big stuff happens today here, at the Centre Spatial Guyanais, the Guyana Space Center in French Guiana. This is the main launch site for the European Space Agency, a close partner in this once-in-a-generation mission, and the home of all Ariane launches. Katie Haswell is there at the launch facility and joins me now live via satellite. Okay, how are things in Kourou, Katie?
Michelle, things are looking really good. The boards are green, the mission controllers are focusing hard, we are go for launch. We've had our eye on the weather the last couple of days. The weather's been a little bit inclement, so we're keeping an eye on that, but otherwise everything's looking absolutely great. And I have to tell you, there is just such a buzz of excitement here in the Mission Control Center. It's a remarkable feeling. Right now we're topping up the tanks on the upper stage of the vehicle. So we've got two great big arms called cryogenic arms, and they clamp onto the upper stage and they pump in the cryogenic fuel, which has to be kept very, very cold. So it has to be topped up right until the last minute because it can evaporate. You'll see those arms kind of falling away just before launch in the last couple of seconds. So up here in the Sky booth in the Mission Control Center, we have NASA's Rob Navius and the European Space Agency's Luce Fabregat. They're standing by. Hi guys, standing by to take on the commentary when we get to about 15 minutes to launch. But right now, Michelle, all the boards are green. We're go for launch. Back to you, Michelle.
We'll be coming back to Katie for the final phases of the countdown in just a little bit. So I'm an astronomer, and this launch is a huge deal for me. I am personally really, really excited. But why is this such a big event for everyone? The Webb telescope is nothing less than humanity's next effort to move closer to understanding some of the biggest questions about the origin of our universe. And it's not just the origins of distant stars and galaxies, but it's the story of us, you and me, how we got here. And speaking of questions, we'd like to include yours in this historic event. On whatever platform you're watching our coverage, drop your questions with the hashtag AskNASA. Later in the broadcast, we'll answer some of them live on air. It can't be said enough that this is a mission for anyone who's ever looked up at the night sky and wonder. People all over the world are sending in their best wishes for the success of Webb, and let's look at some of them now.
제임스 웹 우주만환경 행운을 빕니다.
Boa sorte. Webকে অনেক অনেক শুভকামনা.
Veel succes, Webb.
بالتوفيق لويب.
幸運を祈ります、Webb.
हार्दिक शुभकामनाएं.
We're still on track for a launch at 7:20 a.m. Eastern U.S. time. 2 days ago, the rocket rolled out to its launch pad in Kourou. Of course, there's already been a lot of activity at the launch site. Primary fueling procedures were completed early this morning, preparing the giant Ariane 5 rocket for flight. Let's watch this scene for a moment. We know the world is watching. Today, humanity begins its next bold adventure to extend ourselves out into the cosmos. This is something we do as a whole planet, all of us together. Befitting the global importance of this initiative, let's review some of the basic facts about the observatory shared by people all over the world who are looking forward to the Webb mission.
The entire world is looking forward to the launch of the James Webb Space Telescope. Let's hear more from people around the globe about what makes Webb a scientific and technological marvel.
Será el próximo y principal observatorio espacial para los astrónomos de todo el mundo y llevará más allá los prometedores descubrimientos del telescopio espacial Hubble.
它是一个由美国国家航空航天局、欧洲空间局和加拿大空间局开展的国际合作项目。
Ni darubini kubwa zaidi kuwahi kuwekwa angani na ina nguvu mara 100 kuliko Hubble.
Webb is zo groot dat deze in origami-stijl moet worden opgevouwen om in de raket te passen. Om vervolgens in de ruimte als een transformer te worden uitgeklapt.
Les 5 couches de son écran solaire le protégeront du rayonnement infrarouge émis par le Soleil, la Terre et la Lune. C'est un peu comme avoir une crème solaire avec un FPS de 1 million.
अभूतपूर्व इंफ्रारेड सेंसिटिविटी के साथ ये पिछले 13.5 अरब साल तक के समय में बिग बैंग के बाद सबसे पहले पैदा हुई गैलेक्सियों को देखेगी.
در فاصله 1.5 میلیون کیلومتری از زمین به دور خورشید خواهد گشت، در حالی که تلسکوپ هابل در فاصله 560 کیلومتری از زمین در مدار زمین قرار دارد.
Thousands of people all over the world have worked for years to get us to today's launch. The core partners, NASA, the European Space Agency, and the Canadian Space Agency are the principal players. But a vast core of engineers, scientists, private companies, and more have had a hand in building this one-of-a-kind scientific platform. Without a doubt, this is the most complex spacecraft ever built, with revolutionary technologies, daring mission goals, and a whole lot of personal passion and commitment. We'll hear from our partners later in the broadcast, but first, let's hear from someone representing the science community with a rare perspective about space exploration.
Hello, I'm ESA astronaut Matthias Maurer, currently living and working on the International Space Station ISS. I'm very excited to follow the James Webb Space Telescope's launch with you all from space. Even with the naked eye, we astronauts see that the stars are incredibly sharp and brilliant once we are outside the Earth's atmosphere. James Webb Space Telescope will be the largest and the most powerful telescope in space yet. And it was built to study the big questions. Questions like, where do we come from? How did galaxies form, like our Milky Way? How are stars and planets born, like the Sun and the Earth? Might there even be life on other planets? The James Webb Space Telescope is a joint project between NASA, the European and the Canadian space agencies, and by tens of thousands of people with origins in many countries. And it will be used by scientists everywhere on Earth.
NASA Goddard is the home of the Webb telescope, with big sections designed and built here. But actual mission operations take place here. This is the Mission Operations Center, or MOC, at the Space Telescope Science Institute in Baltimore. After launch, this facility will command and control Webb for the duration of the mission. We'll be looking at the MOC at key moments throughout the broadcast, and this will become a familiar location for viewers in the weeks ahead as the Webb team begins to set up the telescope for work in space. So as we move closer to launch, we'll actually keep a picture of the launch facility right here on the screen. But for the next 10 minutes or so, we're going to talk about some of Webb's principal science goals. If you've ever seen a telescope before, I'm certain it didn't look like this. Of course, the look of this particular machine is a direct result of the scientific questions it's been built to pursue. So fortunately, we've got an expert pair of guests with me this morning to help explain those science goals and much more. So I'm joined now on the set by NASA's Deputy Project Scientist for Exoplanet Science, Nicole Colon, and also with Macarena Garcia-Marin, the Instrument and Calibration Scientist for Webb's mirroring instrument from the European Space Agency. So welcome to you both.
Thank you. Good morning.
Thank you.
So this is our chance to kind of step back and talk about the science goals of Webb. You know, this is the part that really excites astronomers like all of us. And I know that there's unusual things about it being an infrared telescope. There are specific science goals, infrared answers. So maybe you could start us out, Nicole, with you're an expert on exoplanets. How is the infrared really important for your study?
Sure. Well, with exoplanets, we want to study their atmospheres. And as a reminder, exoplanets are planets that orbit distant stars. So we're looking for very small signals when we study their atmospheres. And Webb is this giant telescope that we're able to use to collect these small signals and look for infrared signatures, chemical signatures of water and methane and carbon dioxide, those types of molecules in their atmospheres. And why the infrared? You know, that's really because those signatures are the strongest in the infrared. We know that they exist there, and so that's why we want to use Webb to look there.
It seems an amazing idea. So exoplanets, planets around other stars, are light years away from us, tremendously distant. So how do we know if it's water, methane? I mean, how can we probe an atmosphere so far away?
Mm-hmm. Well, with Webb, there's a couple different ways, but one of the main ways is actually using the transit technique. And this is an indirect method where we actually detect the decrease in starlight that happens as a planet goes in front of its star. But then imagine the planet has an atmosphere. Well, there's an additional decrease in the starlight because the atmosphere blocks some light from our point of view. And why it blocks the light is because there's usually a molecule or something in there, like water and methane, like I mentioned, that is acting as an absorber and blocking the light from our telescope, in this case, Webb.
So going from, the relatively nearby stars and planets, Macarena, you're an expert on very distant things, distant galaxies. So how does infrared contribute to your field of study?
So with Webb, we're going to be able to observe the very first galaxies and stars. We're talking about 3.5 billion years ago, so it's really mind-blowing if you think about it. And why infrared? Well, those galaxies emitted their visible light many, many millions of years ago, and that light travels towards us in time, and at the same time, the universe expands. So in that process of travel and expansion, the light shifted from the visible to the infrared, and so Webb will be able to actually observe those very original primeval galaxies. And not only those, but it will also allow us to observe everything in between, so we can understand the evolution of our galaxies from the first ones to the ones we see today.
This is something kind of amazing. So our eyes interpret different energies of light as different colors. Exactly. And infrared light is a color that our eyes are not sensitive to. But like you said, it's actually just the space of the universe stretching out the light and changing it from visible light into infrared.
Into infrared, exactly.
So how are these first galaxies different from galaxies today?
Well, when you look at the images we have of the oldest galaxies we've seen, they look like fluffier and clumpier. We know they have a lot of star formation, so they are actually, that's a really good signature to measure them. And they are like little seeds that afterwards they merged and got together and evolved until the ones we see today, which are like spirals and elliptical galaxies.
So from, the near universe to the far, one of the things that infrared is very good is seeing through dust. That's another huge advantage. Maybe, Nicole, could you sort of take us through that story?
Sure. With dust, first there's a lot of dust in the universe, but how stars and planets form in the first place, they are forming in these very dense clouds of gas and dust that come together, and it's very difficult to see through them with normal visible light. And so the infrared is actually able to see through that, almost like an X-ray, sees your bones, sees through our skin. You can use the telescope like Webb to see through the dust and see the inner stars forming, or see some newly formed planets that are also very warm from having just formed.
And there's even a possibility of seeing some of the very first stars, or at least some evidence of the first stars that might have existed. But could you tell us a little bit about that, Macarena?
Yeah, so the very first stars, they form right around the time of the very first galaxies, even before that. And so we'll be able to measure them, maybe not the very first one, but the first population of stars, which is really interesting because they were formed out of a very pristine material. And then from there, they evolved into more evolved stars that created all the elements we know today, things like gold, platinum, carbon, everything. Us were formed out of those original stars. So it's a really amazing adventure to observe all these objects and understand them better.
There's so many wonders in the universe, and one of the things that I would never have believed was real unless I'd seen the data with my own eyes is the TRAPPIST-1 system. And that this is actually going to be one of the targets for Webb, is that right? Tell us a little bit about TRAPPIST.
Sure. TRAPPIST-1 is, like you said, it's going to be a target. There are 7 planets in the system, and they're all small, around the size of Earth, actually. So it's also a very compact system. So it's not just that there's a lot of planets and that Webb's going to observe every single one of them, but it's the compact nature that's just really fascinating, because the entire orbit of the planetary systems, like all 7 planets, they fit inside our orbit of Mercury around the sun, and Mercury is our closest planet to the sun. So imagine 7 planets in there, and there's a lot going on, but it's very exciting because we'll get to learn and do comparative science and see, are all these planets, do they have the same chemical signatures in their atmosphere? Do they all have same amount of water, carbon dioxide, things like that?
Well, thank you so much. We're going to be back to talk to you more, but thank you for joining me.
Thank you.
Thank you. Okay. So we'll be back in some more minutes to talk with them. And remember that we're taking your questions, so use the hashtag AskNASA. Webb looks like nothing that's come before because it's pursuing scientific goals like none that have come before. It's taken years to prepare it for flight, and as you might imagine, plans of this scope and scale inevitably run into unexpected challenges. Along the way, just like any of us, it encountered things like snowstorms in the east, wildfires in California, hurricanes that deluged Houston, Texas, and of course the global COVID-19 pandemic, which added its own profound challenges to the whole team. This story really warrants a recap, so check this out.
The Webb Space Telescope presented many engineering challenges, but engineering hasn't been the only obstacle the team had to overcome. In 2011, an outbreak of tornadoes cut electricity to the Marshall Space Flight Center in Alabama for nearly a week, while the team rushed to finish cryogenic testing on the primary mirror segments using power from diesel generators. Engineers had to endure a large snowstorm, known locally as Snowmageddon, while testing the Integrated Science Instrument Module at the Goddard Space Flight Center. And of course, everyone has had to contend with the global pandemic. One particularly memorable challenge was working through Hurricane Harvey in 2017. This massive cyclone dumped 40 to 60 inches of rain across the Houston area over a 4-day period, causing catastrophic flooding and $125 billion of damage, all while the telescope was undergoing cryogenic testing at NASA's Johnson Space Center. Though the telescope remained safe inside the test chamber, water leaked through the ceilings, people had to cover workstations in plastic tarps, food was in short supply, and a few team members trapped by floodwaters had to be rescued by boat. It was rough, to say the least, but the team and the telescope survived the storm. Despite winds and snow and endless rain, the team got it done, and Webb is now ready for its final journey atop a rocket into space.
While the Webb telescope is a technological marvel, everything here began with questions. Questions about how the first stars and galaxies came to be. Questions about whether planets around other stars might have environments that can sustain life. And of course, the promise of discoveries we can't even predict yet. A few days ago, I had a chance to speak with someone who's probably the best person on Earth to help us understand what we know, what we don't know, and how Webb will help fill in those gaps. Dr. John Mather is a Nobel Prize winner who measured the Big Bang with an observatory built here at NASA Goddard. John is Webb's senior project scientist, and we're so pleased to have you here today, John.
Good to be here with you, Michelle.
So to start this incredible story of Webb, let's start with something that's deceptively simple, gravity. There's something special about gravity.
Gravity is special. Gravity always pulls. It's the only force of nature that always pulls. So that's special. And what makes that special is that gravity, although it's very weak, is very long range. It can reach across the universe and slow down the expansion of the material that came from the Big Bang, turn it around, pull it back together, turn it into galaxies and stars and eventually planets and a place where we could live. So that's what makes gravity special among all the forces of nature.
And something so simple, like just the idea that it's always pulling together, that simplicity leads to wonderful complexity, doesn't it?
Yes, because it's always pulling, it's possible for gravitational energy to be converted into kinetic energy, just heat, and the universe becomes self-heating, which is not something other forces could do all by themselves. Clouds of gas can be compressed by the gravity until they get big enough and hot enough to light up and have the nuclear reactions inside that turn hydrogen and helium into the chemical elements you see around you, here in the house, here on the set. So carbon, oxygen, nitrogen, everything we have that we think of as ordinary came from inside stars. So we are stardust, as Carl Sagan told us, but there wasn't any stardust in the Big Bang. So we need this part of the story to be figured out. How did we come to be able to live here on our little planet when the universe started out without all of these goody things?
So you mentioned these planets around other stars. So we're almost sort of going through all these amazing science goals of the Webb. What can Webb tell us about planets around other stars?
Well, once in a while, a planet goes in front of the star, and some of the starlight goes through the atmosphere of the planet, if it has an atmosphere, on its way to the telescope. We will spread out that light into a spectrum, or what you would call a rainbow, and we'll analyze it to see what are the chemicals that are in that atmosphere. So we will be able to tell you, maybe, that's the plan, whether those little planets that might be like Earth actually could have, for instance, water in their atmosphere, and maybe enough water so there could be a liquid ocean under that atmosphere. One of the great questions. So we know they're planets. We know when we should look. We just don't know what we're going to see.
So after the Webb launches, one of my dreams is I'm going to be standing outside in my backyard and point to a star and say there's a planet around that star that we know has water vapor, oxygen, perhaps methane, carbon dioxide. So what is Webb going to also do in the search for life closer to home, our own backyard?
Well, here in our own solar system, we will be looking at everything from Mars on outwards to the farthest we can see. Satellites, comets, asteroids, and the planets themselves. And some of them are really interesting and special because we know they're possible homes of life. What would make a thing a home of life? Well, if it's wet. That's the good clue. So the satellite Europa, which orbits around Jupiter, was discovered by Galileo himself. And we know now that it has an ocean that's covered with ice. There are cracks in the ice where water comes spitting out. NASA are going to send a probe over there to fly through those plumes. We're also going to point over there with the Webb telescope to see what can see about that atmosphere and those plumes of water. We'll be looking at Titan, which is a satellite of Saturn, which is so big that it has an atmosphere enough to fly a helicopter. And it is cold out there, so that what they have, what is on the surface, is solid ice, and over that are liquid hydrocarbons, which you would use for fuel here in our home. But over there, it's liquid rain, lakes and rivers, and we will be looking at the geology of that before we send the helicopter out there.
So you're on this amazing journey from the very distant early universe all the way to our own solar system, but this has also been a personal journey for you. You've been working on Webb since the very beginning of the mission, is that correct?
I have. Since '95, we had our first conversation, but people were even dreaming and imagining way before that what we needed. And you could tell even before we launched the Hubble what were the possibilities, and we learned that we would need an infrared telescope that could do things that Hubble could not do.
Well, John, I've been an admirer of yours for many decades now, and it's an honor to be with you on this part of the mission. So thank you so much for joining us. Best of luck on the launch and the mission ahead.
And thank you for asking all these great questions.
The Hubble Space Telescope delivered profound insights about our place in the cosmos. But perhaps the biggest takeaway from Hubble is that we've only just scratched the surface. Hubble gave us the best ever views of stars and planets forming inside vast, dark clouds of dust. But as soon as we had that data, we were asking new questions that needed better measurements, clearer images. Hubble was also able to capture images from galaxies so far away. Their light took 13 billion years to travel to us. These distant galaxies are just tiny dots in Hubble's images, tantalizing scientists with clues about how the first galaxies formed. In order to pursue a better understanding about the earliest days of the universe, we needed to build a better time machine, and that's Webb. So I'm going to be rejoined here by Nicole and Macarena, and this is our chance to talk a bit about building that better time machine. You know, what about the technology of Webb? So there's so many aspects of Webb to start off with, but maybe again, going back to the theme of infrared. The design of this telescope is so different because we had to use infrared light, heat light. So tell us about some of the challenges of, for example, why does it have to be so cool? Tell us about infrared light in the design.
Right. Well, I think we've heard already just how cool it has to be. It's around or below 50 Kelvin, and that's minus 370 degrees Fahrenheit. Actually, below that is what it operates at. And that's very cold. And the reason we need it so cool is because we don't want the telescope itself to detect itself. Because there's several instruments on board. There's 4 different instruments, and there's some moving parts, and so you need things to be cool, because you want to detect these faint signatures from either an exoplanet atmosphere or faint light from the earliest stars and galaxies. So you just don't want to detect your own telescope.
Now, Macarena, you are the instrument calibration scientist for the coolest instrument.
It is the coolest
on Webb.
instrument, yes.
MIRI. So tell us a bit about MIRI and why it needs to be so cold.
So MIRI, it's a really unique instrument, and it's a great example of this collaboration we have in this mission because it's half European, half US. And so MIRI is the only instrument on board that uses the mid-infrared light. And the mid-infrared light is a bit redder, a bit cooler than the near-infrared light, and so because of that, MIRI needs to be colder in order to detect that very faint signal from high-received galaxies or protoplanetary disks, etc. So because of that, it's the only instrument on board that has a cryocooler. So it is not only the passive cooling from the sun shield, it is active cooling, and it brings it down to about minus 450 Fahrenheit. So it's really extremely cold, a few degrees above the absolute zero.
And we were talking about you don't want the telescope to be so hot that it's basically giving off its own signal, its own radiation, and that leads us to why it needs to be in space, right? So tell us a bit about why do we need to launch this thing into space to see these wavelengths?
Well, again, it kind of goes back to atmospheres because Earth has an atmosphere and there's water in Earth's atmosphere as one example. I mean, there's a lot of other molecules, but basically in the infrared, at the wavelengths that we want to observe some of these stars and planets and galaxies, those wavelengths are actually where Earth's atmosphere is opaque. So with telescopes located on Earth, even at higher mountains where they try to get above the clouds or atmospheres sometimes, there's still residual atmosphere that we're trying to look through and peer through. So in order to see the full infrared wavelength range at a very high sensitivity as well, we need to go to space.
Absolutely. So we talked a bit about some of the power of techniques like spectroscopy. We've heard Dr. John Mather talk about it. So let's go a little bit more into the details of how spectroscopy works and why it's so powerful. Continue.
Oh, sure. Yeah, I can keep going. Well, with spectroscopy, we heard, so visible light, again, is it's a rainbow of colors that we don't see naturally. But if you use something like a prism, you can separate out that light and see all the colors from, blue to red. But then the infrared is redder than the human eyes can see. But you can still do the same technique where you have spectroscopy tools or instruments like Webb has, all these spectroscopic tools, so that we can break up the infrared light and look at certain colors, if you will, so that we can see certain features that we are looking for, whether it's the right wavelength where, a galaxy might be bright or where water is absorbing in an atmosphere.
So Macarena, MIRI has many different capabilities.
It does.
And in fact, it has one that I believe it's something different called coronography as well.
Yes.
Tell us a bit about all these ways that we're going to detect different signatures from planets. Tell us
So
about MIRI.
coronography, it's an amazing technique, but essentially it simulates an eclipse. So when we have a very bright star with planets around, for instance, usually when you take an image, the stars outshines the light of the planet, so you don't see them. But with MIRI and with other instrument NIRCam as well, you can actually block the light of the star, and dim it, and then you see the planets around. And it's really a technique that's going to be very much used and to do, like in this image, direct imaging of planet.
Well, thank you so much. We'll be back to talk to you more with some social media questions. Thank you very much.
Thank you.
NASA and its partners began developing the Webb telescope years ago, growing from an initial inspiration to a design, then schematics, and finally reality. What started as a big dream of studying the origins of the universe required best-in-class engineering expertise to transform into something real. Let's take a short look at the very long story about the earliest days of the James Webb Space Telescope.
Before the Hubble Space Telescope even launched, scientists were already discussing what should come next. Ideas for what was then called the Next Generation Space Telescope evolved throughout the 1990s, and by the end of the decade, NASA had a preliminary plan. Construction of the James Webb Space Telescope began in 2004. Beryllium was mined to create the mirror segments, which technicians polished and coated in a thin layer of gold. Meanwhile, engineers designed and built new science instruments in the US, Europe, and Canada. Every step of the way, there were reviews and tests to make sure each part could withstand the rigors of spaceflight. By the early 2010s, the team began bringing individual components together at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It was there that the mirrors and instruments began to coalesce into the grand machine we see today.
We've said before that the James Webb Space Telescope is an incredibly ambitious mission. Big ambitions come with big challenges, and that's certainly been the story of Webb. From the beginning, the design of this observatory has been a balance between the boldest questions scientists have dared to ask and the cutting-edge technology that our best engineers could offer. The design for Webb evolved from earlier ideas of what a telescope could be, another example of the delicate balance between desire versus capability. To get a better understanding not only of the mission's goals, but also the mechanical guts of the observatory itself, I recently got a chance to speak with a pair of engineers who know the anatomy of the Webb telescope better than just about anyone. I'm here with Keith Parrish, a senior engineer on the Webb mission. And Keith, you brought something to show us today.
Yeah, yes I did. So conceptually, Webb Sunshield is actually quite simple. All we need is 5 tennis court size pieces of this material outstretched to protect the telescope from the sun. So what I have here is an actual sample of that material. This is just Kapton.
It's so light, yeah.
Yeah, it's an industrial, you can buy this and it's commonly used. And what we do is we buy it for Webb, we seam it all together in small pieces, and then we actually coat it with special coatings to give it the what we call the thermal properties we need in orbit. So this one has a nice pink or purplish kind of hue to it, and the reason it's purplish in hue, we use this on the sun side, and we actually put a silicon material on this Kapton, and then we actually put a little bit of a metal in it, and what that metal does is it gives us a nice electrical conductivity. We don't want any surface charging building up, and the other thing is this silicon coating actually drops the temperature of this layer. So, and also it's very durable and can survive, for many, many years in space.
And then this whole thing has to unfold somehow, where we can actually see that behind us.
Exactly right. So if you look at that animation there, unfolding there, so it's actually S-folded up. Almost like a fan. We call it S-folding. And once we get it all folded up, we secure it to a structure by actually pinning it for launch. So, a huge shout out to our mechanical engineer and our entire Sunshield team, because they've come up with some really clever ways to secure this for launch, unfold it, fold it, and then, ultimately get it safely deployed in orbit.
That's wonderful. So speaking of unfolding and all these pins that need to release, let's go over here and talk to James Cooper. You're going to show us what's going on there.
Yeah. Hi. So I have here an example of a non-explosive actuator. We have 178 of these.
These are all these little pins we're talking about, right?
James Webb, right?
Yeah.
107 of the 178 are the membrane release devices. And we use this type of actuator because it produces a very low shock when it's released. And the animation shows conceptually how it works. We send an electrical signal through either one of our connectors. We use both, but either one of them can cause the release to happen. It melts a small wire inside, and then we have a spring that unwinds and allows 2 halves of a split nut to separate, and then our pin can get extracted. And so in the case of the MRDs, it's a spring-loaded pin that pulls to release the folded membranes. In other places, we would be bolting two pieces of structure together and then releasing them so we can deploy them.
And the sun shield itself has 107 of these?
107 MRDs that all have to work.
Every single one has to work.
Every single one has to work. And 178 of this type of device in various configurations around the entire observatory.
Right. Well, if we go over here, we've got something sort of lovely waiting for us, a big gold hexagon. So tell us what we're looking at, a sort of a model here of the mirror segment, right?
Right. A full-scale, single segment, one of the 18 mirror segments on James Webb. The real ones would be machined out of a single piece of beryllium to the exact curvature we need. And then once we're deployed on orbit, each segment can be individually focused to make it act as a single perfect mirror.
Now that coating, tell us about this gold coating here.
Yeah, so this is coated with a very thin layer of gold. It's only a few hundred atoms thick of gold, and that gold is really good because it gives us a reflective property in the infrared, and that's really what Webb is an infrared telescope, and we need that sun shield exists to cool this entire telescope. So this mirror actually runs about minus 400 degrees Fahrenheit on orbit. If it were warmer than that, the infrared energy coming off of this, that heat energy would swamp our detector system and our instruments. So that entire sun shield exists to cool all 18 of these down. And again, this gold coating is what helps with all that reflectivity to make it perform even better.
Well, that's wonderful. So now you put it all together, and we have a smaller mock-up here, the sun shield, the mirror. Tell us what we're looking at here.
Much smaller. So, yeah, this is our entire observatory fully deployed on orbit. And you can see the sun shield here is a large feature. You can see all 5 layers that I talked about earlier. And it's the separation of those 5 layers which lets heat energy escape out to space before it eventually gets to this cold layer. Again, that entire telescope is running minus 400 degrees Fahrenheit, and the way we get it that cold is this side is shaded. The telescope is looking to the deep universe, which is near absolute zero. And then again, this layer here, we've got about a 500 degree temperature drop, so this telescope is also looking at this layer here, which is nice and cold. So that's what lets us, harness thermal physics to cool this down to those really, really cold temperatures. Again, you can see our booms, which are fully deployed and stretching this out, and then ultimately all folds up and gets stowed into this structure for launch.
Right, so the membrane release devices would be along the back side of these structures on the forward and the aft side, and we release them in rows so that we can sequentially start to unfold the membrane once those pins are pulled out of the way.
Well, that's wonderful. Thank you so much for joining us, and best of luck on the launch. I'm very excited.
Yeah, thank you.
Okay, let's get a live launch status update from NASA commentator Rob Navius at the launch site. Rob, how are things in Kourou?
Well, thank you, Michelle, and Merry Christmas from the Jupiter Control Center here in Kourou, French Guiana. You are looking live at an Ariane 5 rocket on its launch pad, ready to send the James Webb Space Telescope on the initial phase of its journey. The fueling of the Ariane 5's first and upper stages began before sunrise, and in the last few minutes, mission controllers here in Kourou and at the telescope's control center at the Space Telescope Science Institute in Baltimore conducted polls, with all positions reporting they are go to proceed into the final phase of the countdown. Launch controllers have been monitoring weather conditions throughout the night, keeping tabs on clouds and wind speeds, both at ground level and in the flight path of the Ariane 5, ensuring that all of the precise commit criteria are acceptable for launch. Right now, we have a green board, no issues as the countdown proceeds, no issues again being tracked by the flight control team here in Kourou. By the way, our broadcast today is a collaborative effort between NASA and the European Space Agency. So that's it from now from the Ariane 5 Mission Control here in Kourou. We'll be back with you soon. For now, let's go back to the Goddard Space Flight Center and Michelle Fowler.
Thank you very much, Rob. So Webb asks big science questions. It demonstrates astounding technology. It inspires and excites people to dream and wonder. And the spark of inspiration is the ignition of creativity. Kids all over the world have a natural affinity for Webb's big pursuits. And now we have a collection of young artists ready to showcase their work.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope. NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb telescope will find.
I believe that the Webb telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun. Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space.
Hello, my name is Gabriel. I am from Romania. This is how I imagine space.
Hello everyone, good morning. This is the drawing of distant galaxy that can be seen by James Webb Space Telescope.
Hi, my name is Anastasia, and this is what I think the telescope will look like, what the telescope will see. I drew the Earth, the Sun, a new planet, a black hole, and stars.
So we've been fielding social media questions from viewers all over the world this morning, and let's take a couple of minutes to share some responses. There's been a couple questions about how long will it take for images to come out, and there's a lot of things that need to happen before the images are coming. So Macarena, why don't you take us through some of that?
Yes, so for the first scientific beautiful images to share with the public, that'll take 6 months. And the reason is because it is, so we launched today. It takes a month to take to the orbit place, to the Lagrange 2 point, and then we have a whole period of cooling down the instruments, aligning the mirrors, and making sure that all the instruments are ready to do science. So the whole process takes 6 months, half a year.
And also all of those 18 segments of mirrors, something needs to happen to get them all working together too, right?
Exactly, because initially you launch with 18 segments and they work separately. So you will take, if you observe one star, you will get 18 little points. So there has to be a process where you take images with NIRCam, which is one of the cameras on board, start moving the mirrors slightly to make them work as a single one, and then by the end of this iterative process, you go from 18 points to a very sharp, pristine single point source. So all mirrors act as a single one.
So let's see, we have a question from LV coming in on Twitter. Will Webb be able to enhance detection of comets, asteroids, or meteors that enter our solar system? So that seems we've got a planetary person here.
Sure. Yeah, well, Webb does have a special observing mode where it's able to track these rapidly moving objects, because compared to these distant stars and galaxies, asteroids and comets, they move pretty quickly. And so Webb will be able to do this so that we can study material that's outgassing from them and learn more about what they're made of.
So let's see, there's just so many good questions, so we only have time for a few more. So one is from Christian Rodriguez on Facebook. How long will it take James Webb to reach Lagrange point 2? And you might also just explain what is Lagrange point 2?
So it takes a month. I think it's actually 29 days to get there. And the Lagrange 2 point is this very interesting stable point. So the gravitational pull between the sun and the Earth creates this point where it is stable, and you can, as we can see there, Webb can orbit around the L2 point in a very stable orbit, only needs a little bit of corrections once in a while, and it can always have the sun shield protecting the telescope from the radiation of the sun. In a full year, you can observe any object in the sky, and it's a continuous observation.
Well, thank you very much. We'll hopefully come back to a few more questions later.
Thank you.
So this is a big mission with a cast of thousands to bring it to life all over the world. As we get closer to launch, let's take a brief look at the main locations where Webb took shape on its journey to space.
Inside the massive high bay clean room at NASA's Goddard Space Flight Center, engineers assembled the 18 gold-covered mirror segments into the backplane of the telescope and integrated the 4 science instruments contributed by international partners. To simulate the harsh environment of launch, they went through vibration tests and acoustic tests. And to simulate a space environment, the instruments endured cryogenic testing in a large thermal vacuum chamber. But it wasn't large enough to hold both the instruments and the mirrors, so the telescope boarded a plane to Houston, Texas, to visit the only thermal vacuum chamber in the world big enough to fit the entire assembly. Chamber A at the Johnson Space Center was originally built to test the Apollo spacecraft, and half a century later, it provided a grueling 100-day test for the Webb telescope. Next, the telescope traveled to Northrop Grumman's facilities in Redondo Beach, California to meet up with its other half, the Sunshield and spacecraft bus. Fully assembled at last, the entire observatory went through yet more tests, many focused on making sure the spacecraft could properly fold up for launch and unfold in space. Then in September 2021, Webb caught a ride on a specialized cargo ship and set out on a 16-day voyage to the European Space Agency's spaceport in Kourou, French Guiana. According to its travel itinerary, that's Webb's last port of call on Earth.
Once Webb gets into space, we're going to have some exciting things to tell you about what happens next, from its extraordinary engineering to the thrilling scientific adventure it's about to enable us to undertake. But launch comes first. And for that, I'm going to turn it over to Katie Haswell, our host at the launch site, and one of NASA's most recognizable voices, launch commentator Rob Navis. It's all yours, Katie.
Thanks very much indeed, Michelle. Well, it's all looking very good here at the spaceport for a Christmas Day launch. Operations running smoothly, the countdown ticking over nicely. All the systems are green and we are go for launch. You can see there we're looking at launch pad number 3, the James Webb Space Telescope, inside the very top of the rocket in first class with its seatbelt on, waiting patiently for liftoff. That's scheduled in about 32 minutes' time. I'm in the Mission Control Center here at the spaceport, the nerve center of operations. We're about 10 kilometers from that pad, and behind me you can see it's a laser focus here in the control center with the mission control centers all on console there as we get closer to launch. We call this the fishbowl behind this protected glass. And up in their skybox here in Mission Control are NASA's Rob Navis and the European Space Agency's Luce Fabregat, and they're standing by to take over the commentary about 15 minutes as we get closer to launch. First of all, though, let's check in on the countdown and let's see how things are progressing with Stefan Israel. Stefan is the CEO of Arianespace. Arianespace is the company responsible for getting our telescope into space today. Stefan, thanks for joining us. No pressure.
Good morning, Katie.
How are things looking?
So we are now 31 minutes before liftoff. So far, so good. Ariane 5 is ready. Webb is ready. The range is ready. And the weather is green.
Well, that's good to hear. So what can we expect to see? What's going to happen?
Yes, so in the 30 coming minutes, we will make the final operations. 10 minutes before liftoff, we will have the final authorization of the weather. And 7 minutes before liftoff, we will enter in the famous synchronized sequence.
And, I mean, how's everyone feeling? I'm guessing everyone's...
We launched for humanity this morning from the Guyana Space Center. You know what Webb is about? After Webb, we will never see the skies in quite the same way.
It's an important project, isn't it, for everybody?
It's a very special mission, but we have delivered already 111 times with Ariane. This is the 112 Ariane 5, so we will deliver this morning.
And everybody there in the control center, cool, calm, and collected. Stefan, thank you very much for having taken time to step out of the fishbowl for us. So you can head back now into the fishbowl and take up your position. Stefan Israel, thank you very much indeed. Stefan, of course, heads up what we call the flight desk, which is the authority that takes all the final decisions in the event of unplanned situations. Now, we are in French Guiana. We're on the northeastern coast of South America. We're in Amazonia. It's hot. It can get a little bit sweaty sometimes, and there are lots and lots of mosquitoes. But somebody who knows it very, very well is Raphael Chevrier. Raphael is a rocket science scientist, or a rocket expert at least, from Arianespace. Thanks for joining us, Rafael. Tell us a little bit more about French Guiana.
Well, French Guiana is a French territory that borders Brazil. It's located in the Amazon rainforest. 97% of the land is covered in trees, so that's why it's so green and beautiful. And you can totally imagine that the wildlife there is absolutely incredible. This is actually one of the best preserved habitats in the world.
And of course, it is in the jungle, and yet it is actually the European spaceport. So what makes this location in South America so important and so relevant?
Well, there are several reasons for this. First, we are on the coast. It means that we can launch over the sea from north to east without having to fly over inhabited area. So this is very convenient to reach any kind of orbit. There is no hurricane here, big tropical storm, there is no earthquake, but more importantly, we are very close to the equator, so that we can benefit from what we call the slingshot effect given by the rotation of the Earth. So let me take this globe. Basically, here on the equator, we are all traveling at roughly 1,000 miles per hour. That's very convenient. Of course, we don't feel it. If we were on the poles, that speed would be very, very close to zero. It means that when Webb is right now on the launch pad, inside the fairing of the Ariane 5, it's already traveling in the right direction, and we can use this extra boost to get us into space. That's also very convenient for Webb, because doing so, it can save its fuel and increase its operational life in orbit at 1.5 million kilometers from here.
And that really is important, 1 million miles, isn't it? And so there's a real proper slingshot effect.
Yeah.
And the facilities here are ultra high-tech, and that's exactly what Webb needs, isn't it?
Yeah, that's very convenient for Webb. It's also located in a nature reserve. So this is the perfect meeting between nature and technology, and people come from all over the world to work here. But one thing that's been very important for Webb is cleanliness, because you know that one speck of dust could alter the vision of the observatory in space. That's why we have been extremely careful in keeping a pristine environment in all our facilities, from Webb's arrival in French Guiana to sealing it inside the rocket.
So let's talk a little bit now about the Webb Space Telescope. I really don't think you need me to tell you that it is the product of a feat of human ingenuity. And you don't get to make a telescope as complex as the James Webb Telescope and as remarkable without tremendous amount of collaboration. And the James Webb Space Telescope is indeed the product of a partnership between 3 space agencies who came together to create it. NASA, the European Space Agency, and also the Canadian Space Agency. So here to talk about that now is Greg Robinson from NASA. Greg, thank you very much for coming to the floor, out of the fishbowl as well for us. And we're talking serious teamwork here, aren't we?
Yes, Katie. We've benefited from an amazing partnership with the Canadian Space Agency and the European Space Agency. Over the life of the development, we've had more than 10,000 people actually touch Webb, 29 states in the U.S. and 14 countries across the globe, and not to mention the amazing industrial base across the globe that have benefited here. In order to do bold missions like this, it takes lots of resources and lots of expertise, so we maximize everyone's expertise.
And how did this bold mission get onto an Ariane 5 European launcher?
So as part of the partnership, the Canadian Space Agency contributed science instruments, and they're incredibly important for this mission. And so did ESA, science instruments, and the amazing Ariane 5 that we will see take us on this journey and put us in the right direction to get to Lagrange Point 2, and we're looking forward to that.
It's a tremendous atmosphere here, isn't it, in the Mission Control Center? There's a real buzz here today. I wonder how you must be feeling, Greg. I mean, it's got to be a very, very emotional time knowing that your telescope is sitting there on top of the rocket, getting closer to launch.
It's certainly amazing. Often talk about the butterflies, and people keep asking me, have they started? Have they started? And yes, they're starting. And when we get to about 20 minutes out, they will start flying a lot. So
well,
the excitement is just amazing.
The excitement is building, and of course everyone very cool, calm and collected. Thank you. Greg Robinson, you can take your position back in the fishbowl now, because I know you've got a lot of work to do in there. Greg Robinson, thank you very much indeed for joining us. So the Ariane 5 launch vehicle is the heaviest lifter in the Ariane 5 Ariane family of launchers. And Raphael, she has got an incredible track record, hasn't she, of success?
Yeah, this is a very reliable and successful rocket. Webb is going to be the 112th Ariane 5 to be launched. And the very first Ariane, the Ariane 1, took off exactly 42 years ago. Yesterday, this was on Christmas Eve, 1979. Good symbol.
Yeah, and hopefully we're going to get a good Christmas present today as well. And I mean, the rocket is also, you don't get to build a rocket like this without collaboration either, do you?
Of course, just like Webb, actually. In fact, 12 different countries have been participating in the development of the Ariane 5, with Ariane Group now being the industrial prime.
And we have a scale model right next to you, Raphael. Why don't you talk us through it? The rocket is made of sections, and we often call those stages, which is what you might hear during the commentary.
Exactly. So first you have the two boosters, solid boosters, that are located on each side of the rocket. They will provide the main thrust in order to literally push the rocket against the gravity of the Earth. Then you have these big tanks that form the main cryogenic stage, with the main engine Vulcan at the bottom.
And then you have the Webb telescope right at the top, inside the fairing.
It is right there on the launch pad, and together they are put on top of the third stage, a cryogenic stage, and it is this upper stage that is going to place Webb into orbit.
And what about the engines? What are we going to see at liftoff?
At liftoff, we first see the main Vulcan engine ignite first. We do this because we want to check it's working properly before we switch on the solid boosters 7 seconds later. Once it's done, there is no turning back. The rocket is going to lift off. And so, yeah, that's very, don't be surprised. Don't be surprised if you don't see the rocket lifting off for 7 seconds. That's time for the rocket to actually warm up before soaring into the sky.
So once we light the touch paper, you can count to 7 before it actually lifts off. Now, one of the advantages of the Ariane 5 vehicle is that it can be modified, and that's exactly what we've done for today's launch. We've had to make some changes for it to be able to host the Webb satellite. And joining me to talk about that is somebody who, the right person for the job indeed, because he was in charge of those changes, Daniel Deschambre from the European Space Agency. Thanks for joining us, Daniel. What did you have to do?
First, we need to recall that Webb will be the largest payload to be ever accommodated on Ariane 5. It fully occupies the volume of the fairing, with gaps as small as 10 centimeters for a diameter of 5 meters. It is the reason why we had to develop a specific integration procedure to ensure that there is no contact with them. After separation, during separation, the venting system of the launcher has been improved in order to balance as much as possible the inside and the outside pressure of the fairing. And this is due to the fear of a depressurization shock, which could damage the delicate layers of Webb submerged shield. After separation, due to the fact that some equipment of Webb are very sensitive to sun exposure, the roll control of the launcher will be tuned in order to make sure that Webb is always oriented only one face to the sun. And in addition, to avoid any hot spot, the launcher will create some oscillating movements, like a barbecue mode, to avoid any overheating. And after Webb separation, there will be a specific end-of-life maneuver to be applied on the upper stage in order to put it on a liberation orbit around the sun, in order to avoid collision in the long term.
Thank you very much indeed, Daniel. So we'll hopefully see the upper stage rocking in space. Not quite all the way around like the familiar barbecue, but a slightly different movement. Ladies and gentlemen, thank you very much indeed for being with us today. I know that you're busy. You've got jobs to do inside the fishbowl, so I'm going to send you right back there now, and very best wishes for the launch. Thank you.
Thank you.
Our telescope has a long journey ahead of it. It's got to travel 1 million miles to its destination in space, its working zone, where it's going to start telling us all about our universe. It's already started that journey because it's traveled to the launch pad from Los Angeles. After final tests were concluded in Los Angeles, Webb was packed into a special container and transported along the LA 405 freeway, which had to be closed because it's so big. It traveled on a special ship. A lot of spacecraft will come to the French Guiana launch site by plane, but Webb was too big for that, so it had to travel by ship, and it went through the Panama Canal. Up through the locks. And it took 16 days to get to the port in Kourou, where it was unloaded and traveled to the spaceport. That's not the real Ariane 5, that's a model, just outside the Jupiter Control Center, actually. It was unpacked very carefully in the facilities that Raphael was talking about. And then fueling started, and of course, the teams had to wear special suits because that's a dangerous job. And then it was placed all the way on top of the Ariane 5 rocket. It was encapsulated inside the fairing and sealed, and then it was rolled out to the launch pad 2 days ago. From the vehicle assembly building to the pad along very special rails. Very, very slowly through the Amazon rainforest. It was raining at the time, and that was 2 days ago, and here we are now. 17 minutes and 46 seconds to launch and counting. All systems are go here at the European Spaceport in French Guiana. We have 3 control centers on the job today. We have the Mission Control Center here. We also have the Launch Control Center, which is about a mile from the pad. And then we also have the Telescope Control Center, Mission Control in Baltimore in the US, and that's where the operational teams are standing by to take over the telescope operations. Once it's released from the mothership, that will be about 27 minutes after launch. And they'll be controlling the Webb telescope for the rest of its life. Very important job. The James Webb Space Telescope is a truly remarkable observatory. People have been working on it for over 2 decades. Some people have been working on it for their whole professional lives. Thomas Zurbuchen is the head of science at NASA, and he's joining me now just to talk about it. Thomas, or Dr. Z, as we can also call you. The day has come. All these decades, all this time, all these people working on the telescope, and here we are, 16 minutes and counting to launch. It's a big day, huh?
Oh, I'm so amazed, right? We have this telescope on top of this rocket, a telescope that 10,000 plus people have worked on in many ways, and together with that telescope, all the hopes and dreams of those individuals and also tens of thousands of scientists, some of them not even born, that will benefit from these data are there with them waiting for these last minutes of countdown for its journey to space.
I'm guessing people are feeling a combination of emotional excitement. What's going through people's minds, do you think?
Oh, I think there's a tremendous sense of accomplishment. Whenever you're on top of a rocket, many things went really, really well. There's tremendous pride. There's always a little bit of anxiety. We know launching is hard. We have one of the absolute best teams in the world working on this right now, so I'm confident in that. We're super excited. I mean, it's just an amazing day today.
And what are you most excited about, Dr. Z?
Well, I'm a scientist, so for me, besides the technology that really is a marvel, I mean, it's really the best we can do. What I'm thinking about is really looking at the universe in new light. We have never seen the universe how Webb will show it to us. And can you just imagine going back in time, 13.5 billion years? It boggles your mind, even as a professional astrophysicist. Kind of just think about all the new things we're going to learn about our most beautiful universe.
Dr. Z, thank you very, very much for joining us. And I want to wish you and all the teams, everybody, the very best for today's launch. Thank you.
Go Webb.
So, yes, indeed, go Webb. So we are now 14 minutes and 30 seconds to launch. We're getting really close now. Everything's going well. All systems are green for launch. And I'm going to hand you over now to NASA's Rob Navius in the skybox alongside the European Space Agency's Luce Fabrichet, who are going to take on the commentary from here on in. Over to you guys. Rob.
Well, thank you, Katie. Merry Christmas to our worldwide audience from our broadcast booth high atop the Jupiter Control Center here in Kourou. Joining me today for this historic launch, my colleague Luce Fabrichet, the head of infrastructure and value chain for the European Space Agency. Luce, good morning.
Good morning,
great to be with you. Great to be with you today.
Very pleased to be here with you and all of you watching us for this very special event.
Well, at this hour, countdown clocks are ticking backward. We are at T-minus 13 minutes, 32 seconds and counting. Out on the launch pad, everything is in great shape. Don't let those clouds fool you. We are go for launch. The latest weather briefing just completed indicated that all weather parameters are green. We have a green board here in the control center, and everything has gone extremely smoothly in the countdown. About 9 minutes ago, a major milestone passed as the James Webb Space Telescope began the process and completed the process of receiving commands to transition from external power to internal battery power following the latest in the series of those weather briefings. Webb will remain on internal battery power until its singular solar array unfurls about 30 minutes after launch. Earlier, telescope controllers reported good environmental readings from sensors inside the fairing encapsulating the telescope atop the upper stage of the Ariane 5 rocket. And Luce, as we enter the most critical phase of the countdown, can you outline some of the upcoming critical activities as we head into the phase called synchronized sequence?
Yes, Rob. We are now reaching the end of this 11-hour sequence that we call the chronology, and that started yesterday evening. All systems here have been prepared for the final launch operations. And at the time being, it's rather quiet now inside the launch table and also inside the launcher. We were told a few minutes ago by the launch control center here that the launcher fluids and electric systems are ready for the final automated sequence. They are on hold now, waiting for the last weather report at minus 10 minutes. After this weather report, 3 minutes later, we will have the beginning of this famous synchronized sequence when all systems will be made ready for the liftoff. This sequence will first be run by the ground calculator, and then the onboard computer will take the lead step by step, and the launch vehicle will be made autonomous from the ground system. You know that we have 2 tanks in each cryogenic stage, upper stage and main stage. All 4 tanks are, of course, thermally insulated from the hot environment we have here in French Guiana. However, these liquid propellants are at very low temperature, and because of that, slightly evaporate. And to ensure they are perfectly loaded at liftoff, their final loading and topping up will last up to 4 minutes before the launch. So that will be the beginning of the synchronized sequence run by the ground calculators. Then we will have on the fleet side the end of the topping up, the final loading and the topping up of the different tanks. And on the electrical side, we will have the onboard computer getting prepared for the launch also, and it will be uploaded with the H0, with the H0 time, the time for the liftoff, which is today at 9 at the beginning of the window, 9:20 local time, 7:20 Eastern time.
And Luce, we're coming up on that final weather report. We expect all systems to remain green. We'll be going down to the fishbowl to confirm that just a moment or two from now. It's a 27-minute ride to orbit from liftoff until the time that the Webb Observatory is separated from the upper stage of the Ariane 5 rocket. Several minutes later, the commands will be given to unfurl its solar array, followed by the confirmation from the telescope controllers in Baltimore that we are power positive, meaning that electrical current is flowing through that solar array. With us today inside the so-called fishbowl, seated with mission controllers on the floor of the control room, is Raphael Chevrier of JamesWebbSpce. Raphael, how's everything looking? What's being discussed down there?
Hi, Rob. Well, so far, so good. We just received the last weather forecast. It's all green for the H0 that is forecast right now. What we checked was altitude winds, wind in the vicinity of the launch pad, and risk of lightning. So right now, it's a relief because the weather was a bit tough in the last couple of days. But right now, everybody is very focused on the next steps. The start of the synchronized sequence at 7 minutes before liftoff. Last operations that Luce described earlier before Webb and the Ariane 5 are going to lift off and soar into the sky.
Thanks, Raphael. We'll be back with you and Luce here shortly. We now have confirmation from Baltimore that James Webb is on internal power. Amidst all of this activity, we cannot forget that it is Christmas Day. 53 years ago, the astronauts of Apollo 8 completed their 10th and final orbit of the moon after reading from the book of Genesis on Christmas Eve to billions of people watching with rapt attention back on our planet. The astronauts then headed for home following their spacecraft's trans-Earth injection burn. Today, more than a half-century later, we're just minutes away from another Genesis, the genesis of new era of discovery. The launch of the James Webb Space Telescope is at hand. We're just 38 seconds away from entering the critical synchronized sequence. You're going to be hearing all the critical calls from the DDO, the Range Operations Manager, who is Jean-Luc Voyer, here in the in the Mission Control Center. There he is. He will be calling the start of synchronized sequence, all of the critical countdown milestones, and we will be listening very intently for his calls. Let's stand by.
À tous de DDO, attention pour la séquence finale lanceur. Top à 0-7 minutes.
And with that, we've entered the period of synchronized sequence. You heard Luce Fabregat just a moment or two ago explain some of the critical activities, the first one coming up just a few seconds from now, which will be the topping off of the main stage tanks. The first or core stage was loaded earlier this morning with 175 tons of propellant, 150 tons of liquid oxygen, and 25 tons of liquid hydrogen. The upper stage loaded with 15 tons of propellant. That will be the workhorse for a 16-minute burn to lift James Webb to its final orbit. At separation, some 27 minutes and 7 seconds after launch, James Webb will be at an altitude of about 864 statute miles. To put that into perspective, some 520 miles higher than the Hubble Space Telescope and more than 600 miles higher than the International Space Station. Webb at that point will be traveling about 21,000 miles an hour as it heads out to a highly elliptical halo-like racetrack orbit some 1 million miles from Earth to begin its scientific observations.
In a little more than 1 minute from now, we will see the 4 tanks pressurized at their flight level for the last tests before the ignition of the Vulcan engine. And in parallel, the electric system are also set in flight configuration. The onboard computer, the electrical power, as for the telescope, it will switch from ground to internal power 1 minute before the launch, 1 minute and 5 seconds before the launch. And we are going to see -6 seconds. At -6 seconds, we will see the disconnection of the upper stage, these big cryotechnic arms you can see on this picture. Then, 3 seconds before the H0, the inertial platform that will give all the information about where it is to the launcher will be released. And at H0, the 7-second sequence to ignite the Vulcan engine of the main stage will start. That will take 7 seconds, a little less than 7 seconds, where the engine will start up to its flight regime. Once the computer has checked that the Vulcan engine is running normally, and you will see at that point a flame going stable at the outlet of the nozzle, and at that point the onboard computer will ignite the 2 boosters that will enable to move the 770 tons of Ariane and Webb.
Coming up on the T-minus 4 minute mark right now, just a couple of milestones real quick. At the 1 minute 5 second mark into the flight, Ariane 5 will go through the period of maximum dynamic pressure, max Q as it's known. That will be the period of maximum aerodynamic forces on the rocket itself. The solid rocket boosters, which will provide about 90% of the initial thrust off the launch pad, will shut down and separate at the 2 minute 21 second mark into the flight, followed 1 minute and 5 seconds after that by fairing jettison. That will expose the James Webb Space Telescope to the environment of flight for the first time. The main stage separation, or the first stage separation, comes at the 8 minute 47 second mark into the flight, and that will be about a 16-minute burn of that upper stage engine. It will cut off at about 24 minutes 51 seconds into the flight, and then we'll go into a coast phase of about 2.5 minutes to allow any oscillations to dampen out, provide the most pristine environment for the James Webb Telescope before observatory separation. We're coming up on the 2 minute 50 second mark into the flight. Again, you're going to be hearing critical calls down the stretch here from the DDO, or the Range Operations Manager, Jean-Luc Voyer. The weather is go. We have a green board, no issues being worked. NASA officials, including Greg Robinson on the right, carefully watching the telemetry, looking intently at the final couple of minutes of the countdown. Lives have been spent in the preparation of the James Webb Space Telescope that is about to fly.
And Beatrice Romero on his side, on the left of the screen, from Arianespace.
And that is the DDO, the Range Operations Manager, Jean-Luc Voyer, as we have hit the 2 minute mark in the countdown.
The flight will be in 2 phases. You will see the first part of the flight during the solid rocket boosters phase. That will be the atmospheric part of the flight, the atmospheric flight, and the trajectory will be driven by a to reduce the aerodynamic loads, and we will have a very different exo-atmospheric flight after that.
And you were watching a number of people, VIPs and invited guests, moving out to the observation platform that is right next to the Jupiter Control Center as we stand by for the 1 minute call from Jean-Luc Voyer.
À tous les DDO, attention pour moins 1 minute. 0 moins 1 minute.
Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 50 seconds and counting. As you heard earlier, the Vulcan 2 engine will ignite. Turbo pumps will come up to flight speed for 7 seconds, and the command will be issued to ignite the solid rocket boosters. The James Webb Space Telescope will be on its way. T-minus 30 seconds and counting. Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Trajectoire est nominale.
Vehicle performance is nominal. The Ariane 5 rocket continues to fly uphill in nominal fashion. The rumble of the powerful Ariane 5 now being felt here in the control center. 3D animation.
We can hear the noise and feel the vibrations here. You're right, Rob. Yeah, impressive.
13 kilometers in altitude, 7 kilometers downrange, traveling about 0.6 kilometers per second.
Tous les paramètres à bord sont normaux.
The trajectory reported to be nominal by Jean-Luc Voyer, the range operations manager. You can see at the bottom of your screen, the yellow line is the trajectory plot, perfectly overlaid over the green line, which was the pre-launch trajectory. 1 minute, 41 seconds into the flight, about 40 seconds away from shutdown of the solid rocket boosters. Coming up on the 2-minute mark into the flight.
When it detects the threshold on acceleration, not the deceleration, but less acceleration.
Tous les paramètres à bord sont normaux.
Everything is okay. Everything is normal.
2 minutes, 15 seconds into the flight.
When the computer detects this threshold, it will separate.
Séparation des EAP.
Done.
We have confirmation of solid rocket booster separation from Jean-Luc Voyer. This coming at an altitude of 44 miles. The Ariane 5 and James Webb traveling almost 5,000 miles an hour. We have about 1 minute, 5 seconds to go before fairing jettison. That'll be the next critical milestone.
The fairing is there to avoid the satellite being exposed to high temperatures and also high airflows. And as soon as the launcher leaves the atmosphere, as is now the case, the satellite does not need anymore to be protected, and Webb does not need anymore to be protected. So each kilogram being very important for the performance of the launch, we are going to eject this no more useful fairing.
And let's go down to the floor in the Jupiter Control Center to Raphael Chevrier of JamesWebbSpce. Raphael, so far so good.
Hi, Rob. So far, so good. Everything is nominal, as we say, when attitude and trajectory of the Ariane 5 is going perfectly well. As you can see also on the yellow line on the screen, we had the confirmation of the separation of the two solid boosters and now of the fairing, meaning that we have crossed the limits of the atmosphere. So everything is going super good. And the DDO just said that all parameters are going perfectly smoothly. So let's continue the mission.
And Raphael, this is a view from the upper stage camera called the Vicky Cam, looking back at the James Webb Space Telescope. This is on about a 20-second delay or so because of the way the imagery is processed here in the control room. There's your telescope ready to unfurl its wings, basically, and begin its journey to the Lagrange point, the L2 point, about 1 million miles away from Earth.
La trajectoire est nominale.
Trajectory is nominal. The report from Jean-Luc Voyer. The liftoff time confirmed here in the Mission Control Center at 12:20 Greenwich Mean Time, 9:20 a.m. Peru time, 7:20 a.m. Eastern Time. The Ariane 5 and James Webb, 181 kilometers in altitude, 450 kilometers downrange from the launch site here in Kourou.
Flight control is very smooth.
5 minutes, 12 seconds into the flight. We have about 3.5 minutes to go in main stage or first stage performance. And again, you can see at the bottom of your screen the yellow plot line overlaid over the green line, meaning we are right on course, right down the pike, and a perfect trajectory so far for the Ariane 5 rocket.
All telemetry data are now received by the Galileo tracking station, which is close to here, where we are in Kourou. It will track the launcher up to the ignition of its upper stage. And then we'll have the natal station in Brazil, Ascension as you can see on the map, in the middle of the ocean, and the two last stations in Africa, Libreville and Malindi, one on the east coast, the other one on the west coast. And the one on the west coast, Malindi, you can see that the telescope will be separated more or less over this Malindi station. And this Malindi station will also acquire the telemetry data from the telescope. You can see both are green, Galileo and Natal on this animation. It means they are expected to receive the data, and it was confirmed right now by the launch operations manager.
Acquisition de télémesure par la station de Natal au Brésil.
And just confirming now that telemetry is being processed through the Brazilian tracking station. The telescope is also processing telemetry through the tracking and data relay satellite system. As it moves further and further out into deep space, all of the telescope's telemetry and its imagery ultimately will be processed through the Deep Space Network in Goldstone, California. We passed the 7-minute mark into the flight. A perfect ride so far on the Ariane 5. We have about 1.5 minutes to go in the first stage performance. Once the main stage engine is commanded to cut off, it will be jettisoned, and just a few seconds after that, the upper stage engine will ignite, and it will be the workhorse for a 16-minute burn that will put James Webb into its preliminary orbit. About 11 minutes from now, telescope controllers at the Space Telescope Science Institute will be sending commands to prepare James Webb for the initial series of commissioning activities that will lead to the deployment of its solar array and the initiation of generation of electrical power for the telescope. About 30 seconds away from main engine cutoff.
La trajectoire est normale.
Nominal trajectory continues to be the watchword for the day from the Range Operations Manager, Jean-Luc Voyer, as we stand by for main engine shutdown and separation.
Extinction de l'EPC.
Opération EPC. And we have main stage shutdown and separation confirmed here in the Mission Control Center, and the ignition of that upper stage. And Raphael Chevrier down in the fishbowl. So far, so good.
Yes, Rob, we have the confirmation of the separation of the main stage and the ignition of the upper stage. The trajectory is perfectly nominal. This is a very important moment for us because it's always a challenge to switch on a cryogenic engine in space condition, and we are now at 220 kilometers of altitude. Speed is a bit more than 7 kilometers per second. As we enter now the second stage of the second phase of the flight, the upper stage is going to power for about 16 minutes to place Webb on its transfer orbit, and right now everything is again nominal, as the DDO just said.
And a short time from now, the so-called sawtooth maneuver will get underway. Again, like rocking a baby in a cradle, this will be a maneuver to keep Webb's optics protected from overheating, Luce.
Exactly, Rob, like a baby in a cradle. You can see here Webb attached on top of Ariane 5 upper stage with a very specific configuration. Of course, it will be different during its lifetime, but for the time being, its sun shield is folded and not yet fully protecting the observatory. A number of exhaustive studies have been performed by the mission teams in Europe, in the US, on the thermal conditioning inside the telescope and the way the rays of the sun would propagate and interact with sensitive equipment inside the telescope. Maintain this thermal conditioning is really key before separating this telescope. And in particular, we know that one face of the telescope cannot face the sun. That's why and to produce these right thermal conditions inside Webb, a specific roll law has been designed, what we call the sawtooth approach. And if you are watching carefully to these images, you can see this animation. You can see that the upper stage is going 30 degrees on one side, then 30 degrees on the other side, going back and forth this way to maintain this perfect thermal conditioning for the telescope.
It's worthwhile noting that after Webb separates from the upper stage of the Ariane 5 rocket, which continues to perform in excellent fashion coming up on the 12-minute mark into the flight, the telescope controllers will be taking the baton, if you will, from the mission controllers here in Kourou. The first steps will be the opening of fuel valves, a pair of fuel valves, to start flowing fuel to Webb's onboard thrusters. They then will power on the valve drive electronics. Those are powered on in preparation to control and fire those thrusters when required. Webb's solar array is scheduled to be deployed at approximately the 33-minute mark into the flight. Once it is locked in place, we'll get the call that electricity is flowing through the array. That call will come from the Mission Operations Manager, Carl Starr, who's at the Space Telescope Science Institute at Johns Hopkins in Baltimore. Seated right behind him in that control room is Alicia Starr, a pair of stars helping to guide James Webb on its discovery of the stars. Alicia Starr is the lead engineer for launch and ascent events. Once the solar array is deployed and declared power positive, then 3 out of the 4 hold downs for the aft deployed radiator will be released to prevent binding due to the cool down of the telescope's composite structure. The contamination control heaters will be enabled to protect instrument optics on Webb from any water ice condensation as they cool down. The actuator drive unit will be powered on. This particular mechanism helps with heater control of the fine steering mirror, preventing water ice condensation, later to be used to position each of the mirror's segments. All 6 reaction wheels and the wheel drive electronics will be powered on for Webb, and that will be the precursor to the attitude control system using those reaction wheels to maintain the proper orientation with the sun, as opposed to using onboard thrusters. Of course, fuel in those thrusters, very valuable. It's a limited commodity for the lifetime of James Webb's observations of the universe. We're 13 minutes, 55 seconds into the flight. Jean-Luc Voyer, the Range Operations Manager, continues to report a nominal performance for James Webb. And again, Luce Fabregat from the European Space Agency, how is this trajectory being carefully and methodically adjusted to provide the correct parameters in the final stages of ascent?
Yes, Rob, as you can see on this plot, the altitude is slightly going down. It's perfectly normal. The launch vehicle is really on the line where it should be. This decrease of its altitude, slight decrease of its altitude, will allow the launcher to benefit and the upper stage to benefit of the gravity effect and to increase its velocity until it reaches a thermal threshold. It's about to reach it, or even already reached it now, and it will go up. And now it will go up and up to the separation of the Webb telescope. It will separate the Webb telescope on a highly elliptic orbit, but still around the Earth. The telescope will be released, inserted on an orbit around the Earth, with an apogee, a very high apogee above 1 million kilometers.
Trajectory nominal as reported by Jean-Luc Voyer. You see him in that view, 185 kilometers in altitude, some 4,500 kilometers downrange from the launch site here in Kourou, moving at more than 8 kilometers per second, right on the plot, right on the trajectory, everything looking great. We are about 9 minutes away from the completion of upper stage ignition. It's shut down, and then about a 2.5-minute coast phase before Webb will separate. Observatory separation will be called out. You'll be hearing those calls and the initial calls from Carl Starr, the Mission Operations Manager at the Space Telescope Science Institute at Johns Hopkins, through solar array deploy and the declaration of a power-positive spacecraft. James Webb, of course, will be traveling well beyond the moon to a distance of about 1 million miles away from Earth, settling into a highly elliptical, halo-like orbit to begin its astronomical observations. And again, as we mentioned earlier, at the time of observatory separation, Webb will be at an altitude of approximately 864 miles, statute miles, traveling some 21,000 miles an hour. We're about 8 minutes away from upper stage shutdown. The stage has performed as planned. No issues reported. The launch occurring at 12:20 Greenwich Mean Time, 9:20 Kourou time, 7:20 a.m. Eastern Time on this Christmas Day.
Very smooth launch. The velocity you just mentioned is very important, Rob. The velocity you just mentioned at separation of the telescope is very important. It will be slightly below, okay, I give it in kilometers per second, but it will be slightly below 10 kilometers per second, because it's important that the satellite, the telescope, is not inserted on an escape orbit. It will be placed on a terrestrial orbit so that there will be time for the layout, for the early phase operations and the commissioning of the telescope. And that will be, in fact, the upper stage that will leave this orbit and goes toward an escape liberation orbit.
And of course, even though we're still in powered flight, the trajectory, the acceleration, the speed at which James Webb is going towards its preliminary orbit, all modeled in advance and carefully choreographed to maintain as quiescent an atmosphere and environment around the telescope for its ultimate separation from the upper stage of the Ariane 5 rocket, which is about 6.5 minutes from now. .5 minutes into the flight. It's very quiet now here in the control center here in Kourou. NASA officials, European Space Agency officials, JamesWebbSpce officials, all watching telemetry very carefully. And as the upper stage continues to burn nominally and sheds fuel, the acceleration uphill for the James Webb Space Telescope continues to increase as we approach the 20-minute mark into the flight. Again, upper stage cutoff is scheduled at the 24-minute, 51-second mark into the flight, about 5.5 minutes from now.
After the cutoff of this main engine, as you said, Rob, we will have a short ballistic phase, a short coasting phase that will, when the upper stage will rely fully on its what we call the attitude and roll control system, and it will adjust its attitude so that during this small ballistic phase, all the requirements from the telescope are fully met. And that at the separation, when there will be the separation, the conditions will be very smooth and as requested for the telescope. Beginning of life.
Today's countdown was as flawless as you can imagine. The weather was perfect all the way through the early morning hours, through the fueling process of the vehicle. The weather's been a bit dicey here in Kourou over the past few days, but everything fell together on this Christmas Day to send a new present to the world's astronomer. 20 minutes, 40 seconds into the flight.
Trajectoire normale, tous les paramètres à bord sont normaux.
All parameters nominal as reported by Jean-Luc Voyer, the range operations manager. 4 minutes of powered flight remaining.
The telemetry of the launch vehicle is acquired for the time being by the Libreville tracking station on the western coast of Africa. Flight control is nominal. The trajectory is fully normal, fully as expected, as you can see on the plot with the yellow plot over the green one. That is the expected one.
22 minutes into the flight. Less than 3 minutes of powered flight remaining.
Smooth flight control.
And again, as we've mentioned before, everything nominal reported by the range operations manager. As we've mentioned before, this is a long ride uphill for the James Webb Space Telescope to put it at the proper position in the sky so that it can escape from the Earth, basically head beyond the moon towards its final orbit for its commissioning activities that will be the dominant feature of all of the operations from the Space Telescope Science Institute over the course of the next several weeks.
And the launch operations manager announced the acquisition by the Malindi station, as expected, for the end of the flight and the last part of the upper stage flight and the separation of the telescope.
James Webb is about 4 minutes away from separating from the upper stage. And again, at that point, it will be on its own. And again, those milestones that we discussed a bit earlier in the broadcast will begin to be followed carefully by the telescope controllers at the Mission Operations Center, the MOC as it's called, at the Space Telescope Science Institute in Baltimore. One minute of powered flight remaining. The upper stage continues to function perfectly. It's been a smooth ride for the James Webb Space Telescope.
Trajectoire est nominale.
That upper stage was loaded pre-flight this morning with 15 tons of propellant for this long 16-minute burn. Now about 30 seconds away from upper stage cutoff. And we're standing by for upper stage shutdown and the cutoff of the upper stage engine.
Extinction ESC. Les paramètres à bord sont normaux.
The extinction of the shut-off of the cut-off of the engine was confirmed exactly as expected, with the exactly expected altitude and speed and velocity. So now we have entered the coasting phase, the ballistic phase, that will last for a little more than 2 minutes.
And the telescope controllers in Baltimore confirming that all of the function parameters for the James Webb Space Telescope have been loaded on board the telescope. We are expecting Webb separation at the 27-minute 7-second mark here into the flight. Just over a minute from now, springs will gently push Webb away from the upper stage of the Ariane 5. As it moves further and further away from the upper stage, there'll be what we refer to as a collision avoidance maneuver.
Yes, Rob, exactly. The springs already will give some distancing, of course, between the two objects, between the telescope and the upper stage. And then the upper stage will leave the trajectory of the telescope and makes a special maneuver to pass the telescope and heads towards a liberation orbit and leaves the telescope on its orbit without any risk of collision and without any risk of pollution towards the telescope.
And we're about 17 seconds away from Webb separation.
Séparation Webb Space Telescope. Go Webb!
We do have confirmation of observatory separation. The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery. It was a perfect ride to orbit, and all of the separation sequence events are running in good fashion according to the telescope controllers. And there is the view from the upper stage camera on the Ariane 5 looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
Fantastic pictures of this telescope.
Go Webb, go Webb.
Yes, go Webb.
Ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
Yes, you're right, Rob. Impressive, fantastic pictures. Yeah.
Now we'll be hearing shortly from the Mission Operations Manager at the Space Telescope Science Institute, Carl Starr, who will be calling out the procedures that will lead to the deployment of Webb's solar array. And down in the fishbowl where there is jubilation, let's go to Raphael Chevrier of JamesWebbSpce. And before we do that, Raphael, a bit earlier than planned, but there is the solar array having been deployed. James Webb now has its array out as we stand by for confirmation that it is power positive.
Hey, Rob. J'entends pas ce qu'il me dit. Il m'a appelé ou pas? Il m'a appelé ou pas, Rob?
Non, il t'a pas appelé.
And there it is. There's your critical call. James Webb not only has legs, but it has power as it begins its journey and the commissioning activities to follow. And with that, let's go down to the floor in the fishbowl and Raphael Chevrier of JamesWebbSpce.
This is it. We have witnessed the confirmation that Ariane 5 have safely delivered Webb into space. The upper stage is now being placed on a safe escape orbit around the Sun, but honestly, I've got to tell you that these images are absolutely incredible, and well, it may be the end of the mission for Ariane Space, but it's only the beginning of the journey for Webb. It's now on its way to the Lagrange point. Congratulations to all the team involved in the flight. Really, there is no words to describe the immersion that is happening right now in the fishbowl. So all I can say is good luck, Webb, and bring us incredible data from the deep universe.
At that point, our sequence will continue.
Well, Raphael, congratulations on a perfect ride to orbit from the Ariane 5 out of Kourou here today. A view here in the Space Telescope Science Institute. Their work just beginning on a new era of scientific observations. Luce Fabregat, it was a smooth ride to orbit. Everything went by the book, almost like a simulation, without any problems. And we thank you for all of your insight throughout the course of the day.
Thanks to you, Rob, and really a great achievement. I have many faces and names now coming up to my mind, and really you can be proud of what was achieved on both sides of the Atlantic Ocean. Thanks a lot to you.
Tremendous jubilation here in the control center. You're looking at Jean-Luc Voyer, the range operations manager. Quite a Christmas present for the world's astronomers as the James Webb Space Telescope begins its life heading towards deep space. With that, we're going to go back to the floor now to Katie Haswell. Katie, we did our thing. It's up to you now.
Oh my goodness, I just can't tell you. It's such utter jubilation here on the floor in the Jupiter Control Center. Everybody's been whooping with joy. The controllers here and the mission controllers jumping up, clapping, whooping with joy, people hugging. And I have to say, my throat was caught as I saw the glimpse of sunshine on Webb solar panels as we watched it heading out into space on its journey to its working zone. It's going to take about 6 months before we start getting our deep space observations from Webb. Of course, the teams have got a huge amount to do before we get to that, and our best wishes with all those teams in Baltimore. I want to get some reaction. Right now, everybody's talking and hugging each other because they're feeling so excited, and I totally understand that. Let's start, though, by going over to the NASA administrator, Bill Nelson. Sophia. Okay, can you go on right now?
Okay.
Administrator Bill Nelson right now looking at these jubilant scenes here in the Mission Control Center in Kourou, the European spaceport in South America. There are the teams. The mission controllers have done a fantastic job. It was an utterly flawless launch. from the European spaceport here on the equator in the Amazon rainforest. Hoping to go over now to NASA Administrator Bill Nelson to get some reaction from him.
All stations, 7.5 minutes, give or take, until the sequence continues with our ADIR release part 1 and our TCS configurations.
GSC on off, filling the JW6 config.
The range operations manager has been calling out the milestones throughout the flight today. And the ESA teams responsible for so much fabulous work, great teamwork here to get the Webb telescope into space, and Webb is now heading out on its journey on its own, with the mission controllers, the telescope mission controllers in Baltimore, following those incredibly important first actions and first operations. Charlotte Bezko there, who's responsible for the ESA operations here at the spaceport. We're hanging in there, waiting and hoping to hear from the NASA Administrator, Bill Nelson, who I have absolutely no doubt will be as jubilant as everybody here at the Guiana Space Center. Charlotte Bezko, who has been working for, I think, most of her professional life in human spaceflight, and now heading up the ESA operations here at the European Spaceport. Over to you, Bill Nelson.
Okay, Katie, thank you very much. This is a great day, not only for America, for our European and Canadian partners, but it's a great day for planet Earth. Thanks to the team. You all have just been incredible. And over 3 decades, you've produced this telescope that is now going to take us back in time. It's a time machine. It's going to take us back to the very beginnings of the universe. We are going to discover incredible things that we never imagined. And isn't that typical of this team, where the impossible comes possible? I can't thank you enough on behalf of a grateful United States government. I can't thank our partners in Europe and Canada enough. The French launch team, the JamesWebbSpce, the flawless perfection of the vehicle. And now we have to realize there are still innumerable things that have to work, and they have to work perfectly, 344 of them. But we know that in great reward, there is great risk. And that's what this business is all about. And that's why we dare to explore. The James Webb Space Telescope is very much a part of that exploration. It's significant that we had the delays, and it kept us all the way to today, Christmas Day, when others long ago peered up into the sky and saw stars. But it's also another millennia before that a shepherd grazing his sheep would look up at the night sky. He became a poet, and he penned the words, "The heavens declare the glory of God, the firmament shows his handiwork." That shepherd, that poet, became king. And those immortal words in Psalm 19 encapsulate the expressions that we have today. The handiwork of God as we peer back in time over 13 billion years ago, capture the light from the very beginning of the creation. My congratulations to the team. My congratulations to NASA, to our partners. Go James Webb Space Telescope. God bless you, and God bless planet Earth. Back to you, Katie.
Bill Nelson, thank you very much for those incredibly moving words. Indeed, we're heading out to look at the first light of the universe. And Bill Nelson there, we have Stefan Israel with us from Arianespace. Bill Nelson there being so complimentary about the partnerships, the teamwork, and thanks as well to you guys for this fantastic launch. What a day, Stefan.
Indeed, what a Christmas gift today from the Guyana Space Center. We really want to thank NASA for its trust. The administrator, Bill Nelson. We have with us Thomas Zoburon and all his team, and our first thoughts are going to NASA. It is a journey of 20 years we have made together. We have worked as hell, I would say, to make this happen, and now it's done. I want to thank as well ESA, who is formerly our contractor for this launch. We have Joseph Ashbarer with us. We have Daniel Neuenschwander. We have worked hand by hand to make it happen. I want to thank CNES, Ariane 5 Design Authority, and our daily partner here in the Guyana Space Center. Philippe Baptiste is with us. Marianne Claire is with us. Thank you very much to CNES. For sure, I want to pay my tribute to Ariane Group, which is the prime contractor of Ariane 5, main shareholder of Arianespace, and which has delivered the launcher up to liftoff. And doing so, I pay also my tribute to Arianespace team. The Arianespace team have worked all this year to make this 14th launch of the year and this very special mission. Your dedication, your professionalism has made the success of tonight. tonight is a great step for the space journey. It is also a great step for the friendship between the United States of America, Europe and France. So thank you very much to all of us. And now I think we can take a little bit of a rest, but we are going now to leave with Webb up to its final destination, to the Lagrangian point. Thank you very much. Thanks a lot.
Thank you very much, Stefan. And the Director General of the European Space Agency is JamesWebbSpce. Joseph.
So Merry Christmas to everyone. And we have delivered a Christmas gift today to humanity, to people, to NASA, but also to all the people in this world. Because with this James Webb Space Telescope, we are really enabling new science, new excitement, but also really rewarding all the engineering and all the effort that has gone into it. And I'm really grateful for this success. We have delivered a mission into space. It's power positive, everything is nominal, and I'm very grateful to JamesWebbSpce and all our partners for all this work. Stefan Israel has already thanked all our partners, but let me also just very briefly recall that this was really a team effort. It was a team effort of the European team. We call it Team Europe, the European Space Agency, obviously providing the launcher with JamesWebbSpce, with CNES, with Ariane Group, with all our partners which we have to make this possible. And I really would like to spend a minute to thank all the people involved in this. Today is Christmas. Some of them are here, have been spent weeks here in French Guiana or at the sites where they have been working. It's a special moment. I know you have made sacrifices, but it's a special moment, and really thank you from my heart. But also thank you, NASA. Bill Nelson was speaking before. Thomas Zurbuchen is here with his team. Fantastic cooperation, and this cooperation between NASA and European team is really exemplary. And a big, big thank you, Thomas and your people, for what you have done together with us, that you have entrusted this precious spacecraft to us, which we could deliver. And I'm so happy today, I can tell you, this is a very special moment. It's very nerve-wracking. I couldn't do launches every single day. This would not be good for my life expectancy. But I can tell you this was very exciting, very nerve-wracking, but really, really very successful. And thank you from my side. And congratulations, NASA. Congratulations, science community. Big science is to come, and really, really happy. Thank you from my side.
So the president of the CNES, which is the French space agency, is Philippe Baptiste, and he joins us now. Philippe.
Thank you very much. Well, as everybody here in the room, I'm very, very happy to see that everything was fine, everything is nominal. It's great news for NASA, for ESA, for all of us. I just want to thank all the people who have been working over the last 20 years on this incredible instrument, on this telescope, but also people who have been working on the launch. I'm thinking especially on the 500 people who have been working yesterday during Christmas Eve to prepare the launch, to prepare this successful launch. And I really want to thank them very much. People from CNES, from ESA, from NASA, from JamesWebbSpce, and from all the partners who are around. I also want to give a special thank to the French Armed Force of Guyana who made this launch possible. They were monitoring everything, and without them, nothing would be possible here on this site. So thank you very much for all of them, and thanks also to all people from Guyana who are supporting this incredible European spaceport that we have here today. Thank you very much.
Thank you, Philippe. So we now have a pre-recorded message from Lisa Campbell, who is the president of the Canadian Space Agency.
I am so proud to witness the highly anticipated launch of this extraordinary mission. Je suis très heureuse et fière de m'adresser à vous aujourd'hui. It's a remarkable feat of international collaboration to think of all the scientific and engineering coordination that made today's events possible. In fact, Webb is the result of close to 25 years of planning and development with our international partners. Notre participation au télescope Webb est l'aboutissement de plus de 25 ans de planification et développement avec nos partenaires internationaux. We're playing a big role on the world stage. Canadian excellence has helped make this flagship telescope a reality. Our participation in Webb is extremely significant. It's the largest space science project in the 60-year history of our space program. Webb est effectivement le plus grand projet de sciences spatiales dans lequel nous avons été impliqués depuis le début de notre programme spatial. The successful launch of this groundbreaking telescope bolsters humanity's quest for knowledge of the cosmos and ignites interest in astronomy for a new generation. The Canadian Space Agency is proud to have contributed critical instruments to this large-scale partnership as part of a global effort to spur the next great scientific leap. We're thrilled to take part in a mission of such enormous scientific promise. Nous sommes ravis de faire partie de cette mission extraordinaire. Canadian astronomers are excited to use Webb's data and benefit from the tremendous science opportunities offered by this one-of-a-kind observatory. We congratulate the fantastic team of over 10,000 people who put all their skills, ingenuity, and effort into developing the telescope for more than 2 decades. Bon voyage, Webb! Canadians will follow your journey with great interest.
And now I'd like to hand you over to Thomas de Brucken, who is the head of science at NASA. Thomas.
Well, Katie, what an emotional day, what an emotional time. We're here, all of us who have been working together for so many weeks, months, and years, and more importantly, our teams are taking team images behind us who have put in front of their lives as a highest priority for so many of them to actually get this done and get it done here, working even during the holiday times. I just couldn't be more grateful to the many, whether it's JamesWebbSpce, CNES, the European Space Agency, all the amazing people around French Guiana, the forces that are here, all the good people that have been such great hosts to our teams. All of them I want to thank. You know, whenever we look at launches, they're both an ending and a beginning. They're an ending of an engineering project on the ground, and with many amazing hours and challenges that are there, but they're a beginning. They're a beginning of one of the most amazing missions that humanity has conceived, and I'm so excited to look forward to the next setup of this telescope and all the science to come. Thanks to everybody. This is what we can do when we come together, Katie, as one, humans. It's just absolutely incredible.
It's wonderful. And Dr. Z, thank you very much. Massive congratulations to you all, to everybody who's involved in today. Huge congratulations from everybody here at the Guiana Space Center, and also our very best wishes to all the teams in Baltimore who are now monitoring those early operations of the telescope as it starts to unfold. I'm going to hand you back now to Goddard, but before I do, I just want to say from all of us here at the Guiana Space Center, Merry Christmas. Over to you, Michelle.
Thank you, Katie. I can tell you that here it feels like the dawn of a new age. Historians of the future will divide our understanding of the cosmos into eras before Webb and after Webb. Webb is this milestone that marks a bold effort to look backwards in time to the mysterious origins of everything. Of course, we move at human time scales, so here's what's coming up. In the next few weeks, engineers will unfold Webb's critical sun shield to begin chilling the telescope to unimaginably cold temperatures. They'll extend the DTA, the Deployable Tower Assembly, the structure that supports the Great Golden Mirror. And then finally, they'll unfold that mirror and begin the process of fine-tuning the system for work. Through it all, we intend to bring you live coverage of all of the important events that are happening, along with expert commentary and extraordinary images from the Mission Operations Center and our own broadcast headquarters here at Webb's home, the NASA Goddard Space Flight Center. Stay with us over the next few weeks because the adventure is just getting started. Speaking for everyone on the team, it's been a great pleasure to be with you here today. I'm Michelle Thaller, and you've been watching special live coverage of the historic launch of the James Webb Space Telescope. Thank you for joining us.